Mr. Prasoon Bandyopadhyay. He's an architect with 6 years of experience in IT parks, institutional spaces, and retail design. He graduated in the year 2011 from National Institute of Technology, Patna. He joined L&T Construction in 2011 and worked in various multi-million projects spanning from various IT parks to institutional spaces. Presently, he serves as a lead architect at Future Research Design Company.
Welcome to UGC lecture series. This is AR 6013 Construction Technology and this is lecture number 6. We will talk about construction technology for high-rise buildings today. In this lecture, we will talk about the definition of high-rise buildings. We will go through typical floor construction cycle for high-rise buildings. We will go through simulation models. We will also learn selection of appropriate schedule. Now, what is a high-rise building? High-rise buildings are defined differently by different standards. The Empirical standards defines is as a multi-story structure which is between 35 to 100 meters tall or a building of unknown height from 12 to 39 floors. This is termed as high-rise buildings. The Building Code of Hyderabad, India defines it as a high-rise building is the one with 4 floors or more or 15 meters or more in height. The National Building Code Part 4 Fire and Life Safety defines as all buildings 15 meters and above in height shall be considered as high-rise buildings. The International Conference on Fire Safety defines it as any structure where the height can have a serious impact on evacuation. The Massachusetts United States General Laws defines it as a high-rise is any building that is being higher than 70 feet, that is 21 meters. So, what are the different functions or what are the different parts, different components of a high-rise building? We will talk about the structural systems of tall buildings a little bit. The structural systems of tall buildings can be classified based on the structural material which are used such as concrete or steel. The structural systems of tall buildings can also be divided into two broader categories. One category is interior structure, the other category is exterior structure. This classification is based on the distribution of components of the primary lateral load resisting system over the building. A system is categorized as an interior structure when the major part of the lateral load resisting system is located within the interior of the building. Likewise, if the major part of the lateral load resisting system is located at the building perimeter, a system is categorized as an exterior structure. It should be noted, however, that any interior structure is likely to have some minor components of the lateral load resisting system at the building perimeter, and any exterior structure may have some minor components within the interior of the building also. So, what are the various components of the interior structural system? One is a rigid frame. A rigid frame in structural engineering is the load resisting skeleton which is constructed with straight or curved members interconnected by mostly rigid connections which resist movements induced at the joints of members. Its members can take bending moment, shear and axial load. It also consists of columns and girders joined by movement resistant connections. It can be built up to 20 to 25 floors. Shear wall structure. These are concrete or masonry units that are classified as continuous vertical walls that may serve both architecturally partitions and that may serve as both architectural partitions and also structurally to carry gravity and lateral loading down to earth. Very high in plane stiffness and strength make them ideally suited for bracing tall buildings. It can be usually built as the core of any building and it can be built up to 35 floors. Tube system. The tube system concept is based on the idea that a building can be designed to resist lateral loads by designing it as a hollow cantilever perpendicular to the ground. In the simplest incarnation of the tube, the perimeter of the exterior consists of a closely spaced column that are tied together with deep spandrel beams through moment connections. This assembly of columns and beams forms a rigid frame that amounts to a dense and strong structural wall along the exterior of the building. The different tubular systems are frame tube, brace tube, bundle tube, and tube which is placed inside another tube. Diagrid systems. With their structural efficiency as a varied version of the tubular systems, diagrid structures have been emerging as a new aesthetic trend for all tall buildings in this era of pluralistic styles. The early designs of tall buildings recognized the effectiveness of diagonal bracing members in resisting lateral forces. Most of the structural systems deployed for early tall buildings were steel frames with diagonal bracings of various configurations such as X, K, and chevron. However, while the structural importance of diagonals was well recognized, the aesthetic potential of them were not appreciated since they were considered obstructive for viewing the outdoors. This kind of system efficiently resists lateral shear by axial forces in the diagonal members but have complicated joints. Space truss. As the space truss structures are modified brace tubes with diagonals connecting the exterior to interior. In a typical brace tube structure, all the diagonals which connect the chord members, vertical corner columns in general, are located on the planes parallel to the facades. However, in space trusses, some diagonals penetrate into the interior of the building. What are exoskeleton structures? In exoskeleton structures, lateral load resisting systems are placed outside the building lines away from the facades. Due to the system's compositional characters, it acts as a primary building identifier, which plays one of the major roles of building facades in general cases. Fireproofing of this system is not a serious issue due to its location outside the building line. Super frame structures. Super frame structures can create ultra high-rise buildings of up to 160 floors. The super frames or mega frames assume the form of a portal which is provided on the exterior of a building. The frames resist all wind forces as an exterior tubular structure. The portal frame of the super frame is composed of vertical legs in each corner of the building, which are linked by horizontal elements at about every 12 to 14 floors. Since the vertical elements are concentrated in the corner areas of the building, maximum efficiency is obtained for resisting wind forces. Typical floor construction cycle. In the construction of a high-rise building, one of the planning objectives is to ensure the early completion of the structural frames to generate floor areas for the execution of finishing works, building services, and installation and internal fitting out. So it is imperative that any high-rise building has to be completed within a very fixed timeline. Time is money. So if a construction goes on for ages, we lose money. The builder, the landowner, all the stakeholders are in a state of loss. The contractors, the subcontractors, everybody is in a state of loss. So the completion of any high-rise building has to be done with a proper proper sequencing of activities, and also for that we have to learn that what is a construction cycle of a typical floor. The completion of the structural frames is therefore critical in the overall program. For a building of 42 stories high, as an example, it may consist of 40 typical floors resting on two podium floors. It is not surprised to have construction program aiming at a 2-day or a 4-day cycle for typical floors. It would be a time-cost trade-off in determining the duration for a project in project-wise considerations or in selecting construction methods for major construction activities. It's the role of a planning engineer to balance the resources, inputs, and duration of activities in order to ensure a smooth flow of work sequences and in meeting the project duration and delivering the project on time as per quality standards. In minimizing these construction costs for constructing a reinforced concrete frame, the form work cost is one of the key concerns. It is well recognized that the form work is a temporary work for forming molds for wet concrete. The cost of formwork is highly related to the number of reuse or recycling. It is a general assumption that a set of formwork can be reused for at least 6 to 8 times and 100 times for timber and steel form respectively. Steel formwork systems are prevailing in high-rise building construction because of their durability, good concrete finish and environmental sustainability. However, they are expensive unless the formwork systems are designed to yield a high number of reuse. Taking the above example, a set of formwork for 40 typical floors is still uneconomical. Consequently, it has to subdivide the floor area into zones in order to generate a high number of reuse. The subdivision of a floor into 2 or 4 zones will be a feasible solution. It is obvious that dividing the floor into 4 zones would yield a high number of reuse, that is approximately 160 times if we consider the example that we talked about earlier. The following examples show the arrangement of a 6-day floor cycle for a typical residential block. For example, if we take the example of a construction of a 42-story building, each floor is divided into 4 zones. So, one set of a steel wall form covering the quantity of one zone and 2 sets of slab timber forms with each set covering the whole area of one floor are used. In order to speed up the construction, the precast facades and semi-precast slabs are employed in the construction. The construction cycle aims at ensuring smooth and balanced resource allocation between the trade workers, concreting work and the formwork installation. As a result, the resources rotate horizontally between zone 1 to zone 2 at the same level and move upward to the upper floor in the next construction cycle. The schedule is prepared assuming that the activities are carried out at a constant duration. However, the duration of activities varies due to factors such as supply of materials, skill of workers, weather and efficiency of plant and equipment. So, what happens in a construction cycle? A construction cycle is affected by various factors like we discussed. It is affected by availability of materials. So, if the materials that we are using in the construction are not available locally, it takes a lot of time, it takes a lot of energy, it takes a lot of manpower to procure the materials and bring it to site from one place to another. For example, if the construction is happening at Chennai and the material is available only at Delhi, it takes a lot of logistics in terms of and also lot of money that also adds to the building cost, and in terms of time, and it also adds up a lot of manpower to transport the material from Delhi to Chennai. So, it is always advised that for a smooth or an optimized construction cycle, we need to always use locally available materials. The second is manpower. When the manpower is not available locally or the manpower is not available near the site or is not available on the site or for that particular activity, the time required to do a particular construction activity extends. So, it also impacts the construction cycle and extends it, and thus it impacts the total timeline of the construction cycle of the particular flow. Then the next parameter is weather. The weather also has its own impact. For example, the workers, the construction site workers cannot work in very hot sun, in very high temperature, in rain or in snow. So, weather has its role to play because it is not humanly possible to work on adverse climatic conditions. Then efficiency of plant and equipment. If a manufacturing plants and the equipments at site or at various or the factories which are producing precast concretes, for example, are not good, or the efficiency is not, it's not producing right quantity of materials or proper quality of materials. So, that also impacts the construction cycle of a particular floor. Not only that, but if there is no plan, do, check, act mechanism at the working level, it also adds to a lot of rework in the rework of construction activities, that also builds up a lot of time taken to perform an activity that in turn affects the entire construction cycle in totality for a particular floor and also in totality of the construction of a high-rise building. Material hoisting also plays an important role in high-rise building construction. As the building grows vertically, the transportation time increases and thus extends the duration of crane related activities also. Now, simulation model for typical floor cycle. As we discussed earlier, that there are various activities that are included that are part that play a crucial role in a construction cycle of a typical floor. So, it is very important to form a simulation model so that we can track the completion, the start and completion of all the critical activities that provide us a satisfactory end result in construction. So, the simulation techniques have been used to predict an activity duration and improve planning. However, the building up of simulation models requires planners to have a good knowledge of simulation. Thus, a network-based simulation can be used in this study. It simplifies the skills and knowledge required for modeling a simulation network, as general simulation program can be difficult for general users. What happens is, if we have a complex simulation, it will be very difficult for any person, for example a contractor, an architect, a structural engineer, a service engineer who is on the construction side, a supervisor, a general person, to understand if there is a complex simulation. So, the objective of a simulation model should be to break the activities and to display it in a very simple manner, so that anybody can understand that where a constructional activity is getting delayed, where it is held up, and what he should do to release that activity and close it on time. The planners who have the knowledge in constructing critical path network and bar charts could be able to achieve this simple simulation model. The construction of simulation network for modeling is similar to the critical path network using the activity or node format, except the loops are allowed to show the recycling of resources. So, there are various loops that denotes that this activity, that these resources can be recycled also in a particular simulation model. During the simulation process, the activities may either be inactive if the constraints are met, or otherwise in an idle mode if the constraints still exist. So, in this table, as you can see, this table has activity at the left hand side and the duration. The duration are divided into three parts. One is a mean duration, one is a maximum duration, and one is a minimum duration. So, for example, in these activities, as we go through, there are precast facade fixing, wall steel fixing, wall form fixing, wall concreting, stripping form, semi-precast slab fixing, slab form fixing, beam and slab steel fixing, electrical conduiting, beam and slab concreting. So, all these activities are important for a typical floor construction cycle. So, now in this mean column, we see an average time required to complete these activities. Now, in this maximum and minimum time, it is provided so that we can compute the maximum time, we can judge the maximum time that is required for with all constraints to complete this activity. For example, for this precast facade fixing activity, if an average time required is 1 hour, the maximum time with all constraints of manpower, weather, etc., may be computed to 1.25 hours. And the minimum activity can also happen. There is a probability that the activity happens well before time, and it can take only 0.85 hours. So, such charts have to be prepared in which all the activities have to be listed with proper duration, that is divided into mean, maximum and minimum time required, so that we can compute, we can plan, and we can perform all the construction activities smoothly. The next table for you is a simulation result table. So, in this result, you see there is a breakage of working period, then there are activity durations, and there are cycles, and they are compared with a 6-day cycle. So for example, an activity is happening from morning 8 o'clock to evening 6 o'clock, and the activity duration is constant. That means that it will take only this much of time for an activity to be completed, no less and no more. So if we do this, it will take 6.21 days to complete this activity. So if we compare it with a 6-day cycle, it will take 3.5 days to complete this particular activity. Similarly, if a particular activity happens between the same time, that is morning 8 o'clock to morning 6 o'clock, but its activity duration is variable based on man, machinery and nature, its cycle days is 4.45 days, it may exceed that, it takes more time, that is the time will come in negative, that is 25.8 days probably. So in a 6-day cycle, we will fall back into loss of 25.8 days. This kind of simulation table is required for optimizing the time required to carry out the construction activities for high-rise buildings. Since there are a lot of complexities involved in construction, if we do not do these activities, we won't know where a process is stuck and what needs to be done to ensure a smooth movement of that process to execution. An appropriate schedule. There will be a lot of schedules when we start a construction process, but a selection of an appropriate schedule is very important. The simulations provide alternatives for planners to make decisions on initial scheduling, and subsequently they keep on updating. The simulation results enable planners to locate the upper limit of the floor cycle, that is approaching to the crash time solution, that is maximum time required to complete an activity. However, it is a general rule in planning that the normal time should be used in planning stage unless the project duration would have already been overrun. For example, if the project is already in the closing stage, we cannot use the normal time for concluding an activity. In that case, we have to use the minimum possible time. When deciding the appropriate floor cycle duration, the planners have to review all the factors and the merits prior to determining the strategies as discussed earlier. So, in this lecture, let us summarize what we learned. We understood what are the high-rise buildings, what are the various components of a high-rise building, and what are the critical activities involved in a high-rise building construction. We understood how to plan the various activities while constructing a high-rise building. Now, typical questions can be to elaborate the critical activities in construction of high-rise buildings. There can be a question on explain how to plan the activities in optimum time for the construction of high-rise buildings. Thank you.